I had a tremendous reaction to my lecture Tuesday. All sorts of people came to see me, and I'm reminded of a time when I taught modern algebra, and I had a young man and young woman in my class, and about 10 years later they showed up at MIT, a happily married couple. They had met in my class, and she said, "What a wonderful class that was. You made everything crystal clear and carried out every detail." And he said, "Nonsense. You didn't prove a goddamn thing." That was the range of reaction to my first talk. Pardon?
They still married?
Yes, that occurred to me. The main message last time was adding one category, supersymmetry, and that if you followed that through consistently, then you got a proof of the index theorem for the Dirac operator or Dirac-like operators in a very natural way. Maybe I should give some auxiliary lectures on what supersymmetry is and what supermanifolds are, but the message last time, aside from the details that I was trying to give, was if you, in the category of supermanifolds, if you were to be consistent about superpath integration, what you meant by supercotangent bundle, etc., then you would be led to the super path integral formula for the Dirac operator, and you would quickly get a statement of the theorem. And the proof is a little delicate in showing that the semi-classical approximation was exact. And then right at the end of the hour, I showed that very quickly, if you added the category of superstrings, that is strings, to what I'd already done, then you got something which was quite new, that is in recent times. You got free of charge what's called the elliptic genus in topology. And you got, in that elliptic genus, the modularity of the elliptic genus just from the fact that you were talking about maps of a torus into a manifold, and that the only part of the torus you were using was a complex structure. So I want to emphasize to several of you, I'm not trying to illuminate any physics. I'm trying to show you how some of these ideas in string theory are having some impact on mathematics. Moreover, because of the background of most mathematicians here, and also my own, there's very little we can actually demonstrate. I can only stick to some fundamental principles and use them to illustrate a few items, and I have emphasized these two new categories that we should do things in. Now today I want to talk about S-Duality for abelian gauge theories, and so my strategy in these talks will be to do something that I think is reasonably simple, or at least can be explained mathematically, that is a reflection of something deeper going on in physics. In this case, S-duality for the non-abelian gauge theories. I can only actually do something in the abelian case. So my proposal today is simply to carry out the abelian case and then talk about what it means in the more general context of non-abelian gauge theories and what's been done there, etc. I'm really giving an exposition of a paper of Ed Witten with some modifications to make it more understandable to mathematicians. So for a little while I will do some things that are certainly standard to geometers. X will be compact oriented Riemannian 4 manifold we're going to talk about U1 gauge theory. So we'll have a principal U1 bundle and a line bundle associated, a Hermitian line bundle. These line bundles are classified up to C1, the first Chern class, in H2 with Z coefficients. Let AL be the affine space of connections on this line bundle. If you have a connection, of course, we have its 2 form, and we have the first Chern class expressed as the curvature of that 2 form. We need the star operator on the Riemannian 4 manifold. And we let P plus and minus be the projection on the +1 eigenspace of star and the -1 eigenspace of star, and we let these be the self-dual and anti-dual parts of the curvature. I remind you that the norm squared is this for F for the field, and we can express C1 squared in terms of the difference of the self-dual and anti-dual parts of the curvature. Now, what I want to do eventually is to integrate overall connections with an appropriate action, and here's what the action is. The action is the usual one, the norm of FA squared, plus a topological term, sort of P1, C1 squared in this case, which we can write out in various ways. The important thing here is that we have some coupling constant in front of the ordinary action, the field strength squared, and another coupling constant in front of the topological term. And that, in fact, is going to be the nature, often enough, of all the actions that one considers. There'll be something that is very natural from the physics point of view, and there'll be an added term which is topological, in this case coming from line bundles, in other cases coming from the classification, say, of SU2 bundles. In the more interesting cases in string theory, coming from some topology of fields and their behavior near infinity in various space-times. But I want to emphasize that what makes many of what's interesting these days is a combination of some standard things in physics with some topology and an expression of whatever the topological invariants are, with coupling constants in both. Pardon?
Is that an I in front of the theta?
Yes. There's a phase.
G and theta are numbers.
G is a positive number. Theta is a number, a real number also. And in fact, I am denoting by tau this complex number, and it's in the upper half plane. When we fix L, we will write this action as just a function of A and tau. Now I remind you that for spin manifolds, C1 squared is even. There's a factor of a half occurring here. This should have been 2 pi. If I translate tau by tau plus 2 pi, then it'll be invariant, but in general, translation will be invariant by, instead of 2 pi, 4 pi z, because of the factor 2 above. So the action's invariant under translation by discrete group, either integers times 2 pi or twice the integers. even integers. Now another trivial comment for the moment. Notice, well, first if I look at minus 1 over tau, that's what it looks like. In particular, when theta is 0, minus 1 over tau is this, and so for theta equals 0, g is replaced by 4 pi over g. So when g is small, going to minus 1 over tau, then the coupling constant becomes large, and when the coupling constant is large, if you replace tau by minus 1 over tau, it becomes small. And this is a statement in physics that you're going from weak coupling to strong coupling, or strong coupling to weak coupling. That's very exciting for physics if you can relate two theories by a change of coupling this way, because you know what to look for when the coupling is small, but you don't know what the theory looks like when the coupling is large. So if you can replace your field theory or whatever it is you're talking about by another theory which takes that reciprocal, then you have replaced problems with large coupling in one theory with weak coupling in another theory, and that's a tremendous advance. Now you can see where I'm heading, since I have shown that the action is invariant under translation by an integer, or twice an integer for tau, and I've already looked at minus 1 over tau. That what I'm going to state is a theorem that says you get a modular function. We need a little more machinery to say that. So we'll let chi and tau be the Euler class in the signature, which I express in terms of the beta numbers that way. And we'll say a function z is a modular form of weight uv for a discrete subgroup of SL2z, a finite index, if z at this value is c tau plus d to the uth power c tau bar plus d to the vth power times z of t for this matrix in the subgroup gamma. And as you know, you only have to check this for generators, like tau into minus 1 over tau and the appropriate translation. Now we go to the physics of the situation. We want to consider the function z of tau, which is the sum over all line bundles, and a functional integral, the integral over all connections for that line bundle, of the action I've just written down. We will need to make sense of this integral and see that the sum makes sense as well. The sum will mean over, since we're thinking of the line bundles is determined by their second Chern class. And what we will want to say is that this function, when we make sense of it, is a modular form with weight chi plus sigma over 4, chi minus sigma over 4. That's the statement. That isn't quite right, but it's close enough for the moment that I can stop and say a word or two. The whole point is that, and the reason I've restricted to abelian gauge theories is that whatever the functional integrals are, they're going to be quadratic. They're going to be Gaussian-like integrals, so we can actually evaluate and we can actually see what this looks like. When we come to non-abelian gauge theories, I won't say much about it, but at the end, the whole point is that there's a conjecture, then a corresponding function for appropriate non-abelian gauge theories is also modular. And I'll state what the facts are at the end. But for the moment, I just want to get you accustomed to the idea that you want to think of this path integral or this functional integral as a function of tau, and we're investigating its modular properties.
Are those integers?
What?
Pi plus sigma. Pi minus sigma.
Tau is in the upper half plane, so whether I take square roots or not doesn't matter. I know what square roots are. That's what's bothering u to the power, v to the power. Now the proper definition is, and already you begin to see some complications, that the proper function is not the function we've talked about over here, but the imaginary part of tau, that's 4 pi over g squared, to a certain dimension. That is 1/2 the dimension of 1 forms on the manifold minus the dimension of 0 forms on the manifold times the previous one. So there's a complication already. This is called a counter term in physics. It says that what we want is not quite invariant as in the tau function, as a function of tau of the metrics, and we have to put in a counter term. This counter term is such that we have to regulate what we mean by the dimension of 1 forms and the dimension of 0 forms. We'll come to that. It's part of the exercise here. So for the moment, let's not worry about what those infinite dimensions come down to. So the theorem is that z of tau is well defined, or we can make it well defined, and it is a modular form of weight chi plus sigma over 4, chi minus sigma over 4. So what I propose to do is simply show you how that goes. Naturally, I can't carry out all details, but enough so you see what's going on. And in the process, I have to define what I mean by the functional integral when we come to those parts.
And the duality is the invariance of the inversion. Tau goes 1 over tau.
Pretty
What
much.
do you mean by the duality in your title? So
Yes. Duality means something is modular, or tau goes into minus 1 over tau. That's what physicists mean by S-Duality. Strictly speaking, they mean some duality between two theories where the coupling constant in one theory goes into 1 over the coupling constant in the other theory. So we proceed as follows. So we'll fix L. We're summing over line bundles. We're going to stick with one line bundle. We're going to choose a connection in that space of connections on L so that the curvature is harmonic. That means we've chosen to minimize the norm of f of a squared for all a in a sub L. Easily done. You'll get a harmonic representative for the curvature. Furthermore, then once you've chosen one connection, of course, the space of all connections it's an affine space. Once you've picked one, it differs by the C infinity by 1 forms, C infinity sections of lambda 1. And we can split up the space of 1 forms as the first cohomology, as harmonic, plus d of something, plus d star of something. And moreover, because you've picked the minimum, the norm of f of ah plus mu squared is the norm of our choice plus the complement d mu squared. Remember, we're in the Abelian case, so the curvature of f of ah plus mu is the curvature plus d mu. So this is the sum of two pieces, and having picked the minimum, the norm squared is the sum of the squares. So that means we can rewrite the action factors. So there'll be this term plus, oops, this should have been a mu. I used tau for something else. No, that's right. It's right as it stands. Okay. Now, what I'm about to say, and in subsequent statements, I'm telling you what the functional integral means. The measure dA, it's not really a measure. It's supposed to be Lebesgue measure on that affine space. It's going to be translation invariant. So what I mean by dA is this, and that really means d mu. AH is fixed on that fixed line bundle. So this integral really means we take out the factor that doesn't depend on mu. That's this one. And we're integrating that term. Notice that this term is independent of which line bundle we're at, so we can just factor them out of the sum, and we'll deal with it in a moment. So in the partition function, which was the sum over line bundles, we now have a common factor, which is this path integral over all one forms of something quadratic in mu. That's the Gaussian, which we'll deal with in a minute, but let's see what's left in the sum. We're integrating over h2 of z, that discrete group, this action, which we write out in terms of the curvatures, those harmonic forms of the curvature in the plus and minus part. And we identify C1 with this 2 form. And we consider a quadratic form, Q plus and minus, of elements in H2 as this sum, which is C1 wedged the projection on self and anti-dual for C1.
What's the coefficient of E? Right.
Pardon?
Coefficient, the exponent of E there, not right.
E to the minus I over 8 pi. So if you write this out, a little algebra, you'll see that what you're doing is you're summing over h2xz of e to the minus I pi over 2 of this function of tau. Whoops. For this series to converge, we need the imaginary part of this term, which I'm defining to be q sub tau, that quadratic form, to be negative. And in fact, if you make the What was that?
There's the missing q's. Tau bar q plus c.
Sorry, you're right. Thank you. In fact, if tau is u plus iv, you can compute that you get minus v times enormous C squared. So this is, in fact, negative when tau is in the upper half plane. So we have a quadratic form, e to the minus I pi 2 q sub tau, on h2 of xr, the space of harmonic two forms, whose real part is negative, and the sum over the lattice h2xz converges, giving a Siegel theta function. Now, the point what I've done is perfectly standard in these functional integrals, but the point I want to make is that by factoring out the part that's really a functional integral, that what's left is something that four-dimensional topologists know very well, a combination of cup product and the star operator, and by summing, what happens here is that you get something which is a theta function. And now I'm just going to wave my hands, just because I'm lazy. I have the details if you want them. But if you look at Mumford, this theta function is modular, and it's modular with weight beta 2 plus over 2, beta 2 minus over 2. That's what happens. You're going to get an expression of matrix with tau down the diagonal where the signature of the quadratic form enters, so that you're going to get tau. Its determinant is what you need, and you're going to get beta tau with beta 2 plus times, and for tau, and for tau bar, beta 2 minus times. So I'm waving my hands at that because that's a bit technical, but it's within the domain of well-known mathematics, although I must say I myself lose an eighth root of unity when I look at what's in Mumford, and I can't straighten myself out on that particular point. But, of course, physics at the moment doesn't care about that eighth root of unity. For our purposes, we won't bother.
Those eighth roots of unity arise as a semi-classical approximation. I was looking at the formulas in the book and saw this.
Well, maybe it should be there. As I say, I don't know the answer to that. Okay, now we want to analyze the common factor. That's where the Gaussian integral enters, and that's where, again, this is perfectly routine in path integral formalism, but I'll go over it for those of you who haven't seen it. What we want to do is integrate then this expression over all one forms. Now, the first problem is, of course, that if mu is exact, d mu is 0, and so you're integrating part of it. If you integrate over exact forms, you're integrating 1 over the space of exact forms, and so you're getting infinity. First thing we have to do is avoid that, and the way you do that is you simply project on the orthogonal complement. That's about what I'm going to do, but I'm going to do it a little more consistently in a way that tells you a little of what you would want to do in more general circumstances. Now we have the theta got determined. That was in that sum.
Right, but now this only depends on G.
Yes.
But the rest was already modular. Are you going to say that this is G independent?
No, it will also have some modularity, as you'll soon see.
Only in G, not in theta.
Right. It'll only be in the imaginary part of tau. And in fact, this is where the difficulty is. If you go back, if I can find it. Well, let me go on. It will become clear when I said you have to add a counter term. The counter term is added because of what's about to appear. And that's why in the final end, the theorem is not modularity in terms of B2 plus and B2 minus, but chi plus sigma over 2 and chi minus sigma over 2 because of beta 0 and beta 1 entering. So the group of gates, I remind you the group of gates transformations, these are functions from x to u1. It acts on P1. Now we're in the trivial P1, meaning the principal bundle for the trivial line bundle 1, which is x cross u1, and it acts on this factor. And it sends one forms into this one form, because the I over here, because strictly speaking this is imaginary. Moreover, of course, we have among the gates transformations, we have those which are homotopically trivial, and the full group of gates transforms modulo the connected component is the first cohomology of the space X. Did I put the bottom on here? No. Yo, here. Yeah. I remember we wrote the usual Hodge decomposition for one forms, and then G0 acts on this space by translation here, and the H1 of XZ acts on this space by translation. So here's again a condition or an explanation of what the functional integral means. As I said, I didn't want to integrate 1 over an infinite space. We project down, and what I meant by that, what we mean is the total volume of the projected measure. Here's a measure. I'm projecting it down to the orbit space. That is, on one form's modulo the action of gates transformations. And for what I've just said, what you're going to get is H1 of XR over the lattice subgroup of integral cohomology plus this space, because d of lambda 1 is killed by the translations given by the connected component G0. And then the functional, now that we're integrating over these two pieces, what we have upstairs doesn't depend on here. That's all 1. So what we mean by the functional integral is this volume. It's finite. It's a torus. So it's this volume times the integral of this Gaussian measure over a space on which the action is never 0. It's the whole point of this exercise. Note that this part doesn't depend on tau in any way.
Did you say again?
Mu. Hold on. Let me make a change. My problem is that I've, of course, throughout used tau as the complex number in the upper half plane, but for me often tau is a 1 form. And sometimes I've written tau where I meant mu. Question? Yes, Dennis.
I realize I could be asking 2 questions. The first question would be, pretending that the first thing was finite and made sense, tell me in mathematical terms what you've just done. The second question would be,
Well,
Answer either one and tell me which one you're answering.
yeah, the general answer is this. If you have one of these functional integrals and you've got a large group of symmetries that leave the action invariant, then what you do is, what your integral really means is integrating over the orbit space. That's what I'm saying.
It's okay. Just but okay.
In this case, the orbit space, the whole thing is very simple. It's all linear. So the full space, say, looks like this. The orbit space.
So now you really have a measure.
Yeah. Oh, yes. So in this particular case, here is the full space. The orbit space, except for, let's forget about the part which is the harmonic part. On the orthogonal complement of the harmonic part, the orbits look like this. And you project down, and so you're really integrating over this space. The measure is invariant in this direction. That's the d mu, because these are the exact forms. So you're really integrating over this space. Then for this part, the action of the group is translation by the discrete group, so you would be integrating over this space. What happens in the non-abelian case is a lot more complicated. Then the space A, the orbits look like this. The orbit space is like that. It's actually a curved manifold, and there are problems about integrating over it. And in fact, there's a lot of discussion about taking local cross-sections and integrating over local cross-sections, and then proving that things that you're going to get are independent of which cross-section you get. There aren't any global cross-sections because of the topology, and there's a whole technology here, BRST, which tries to take care of the problem that this orbit space is not a simple product. Now actually Peter's an expert on this, so he's someone that you might want to talk to about this technology. But in our case, it's really very simple, which is one of the reasons I chose it, because we can really explain what's going on. And as you just said, once you push the measure down, now you have an honest Gaussian measure. This is a Gaussian measure on a Hilbert space, and we're going to evaluate it by a certain means. And again, if I wanted to be technical about it, it's within the realm of extensions of Wiener measure, Gaussian measures on Hilbert space, a well-known theory.
Isn't it a red herring for one to have a full cross-section?
Yeah.
It should be some kind of induced measure if the group is unimodular or something like that.
Well, of course,
It wouldn't be if it's not unimodular. Also, problems like that. They're not doing things. Isn't there finite dimensional?
oh, for finite dimensions, there's no problem. This is all infinite dimension. This is a space of connections in the non-abelian case. This is a group of gauge transformations, which is kind of complicated. The quotient is well defined, but it's not even an integral because of reducible connections. And yet you want to integrate over it, and it can't be done technically. If you want to talk about perturbative quantum field theory, then you only want to do this locally in the neighborhood of a point. Then this procedure of taking local cross-sections, see what the measure projects down to, and then you're going to end up with determinants of the map. And as I say, it's a well-defined problem with well-defined procedures for dealing with it, though there's some difficulties with it. So, I'm just going to look at the first line for a moment, and then I'll explain what I mean. What I want to say is that the integral of this measure over the space on which it's not singular, we're now on that horizontal space, the complement of the C means closed, the complement of the closed one-forms, this Gaussian measure, I'm claiming it is the one over the square root of the determinant of this operator, but it should have been the other way around, d star, not d star d. So So let's stare at the first line and let's see why that should be the case and what will I mean by determinant. I remind you of what the basic idea is. If you look at an ordinary Gaussian, that this integral is 1 over the square root of lambda, except for a factor of 2 pi that I'm not going to worry about. If we wanted to integrate e to the minus t dv dv for t a symmetric matrix, then we'll get 1 over the square root of the determinant of t by a rotation, writing t as a diagonal matrix, separating out the integrals and integrating separately. So the idea is that in finite dimensions, t, the integral of this Gaussian is 1 over the square root of the determinant of t. And so all we need in order to say what we mean by this integral, instead of the technical definitions from Wiener integration, is to simply say what we mean by the determinant of this operator. Now I'm going to remind you of that very quickly, because I not only need determinant, but remember I needed what we meant by the dimension of an infinite dimensional vector space. So in our case, what we'll do is take a Laplacian we need which is not 0. So say if we were on K-forms, we would take the ordinary Laplacian plus projection on the harmonic form. So the eigenvalues are 1 where they'd normally be 0 on that space. And we define the regularized dimension of this space as simply the trace of the zeta function associated with that Laplacian to the s power, trace at 0. I remind you that analysis tells us that that function of s is meromorphic in the entire plane, or in a half plane, is holomorphic in a half plane, has extension to be meromorphic in the entire plane, and is regular, has no pole at s equals 0. And the reason we make this definition, you'll see 2 reasons. But the first is that what that trace is the sum over the eigenvalues, and at s equals 0 you're counting each eigenvalue once. So this is a way of regulating that sum, that infinite sum, to be finite. Depends on the metric. because the Laplacians depend on the metric. In the same way, we define the log determinant to be minus the derivative of that zeta function at s equals 0. If you wrote out the eigenvalues, it's this sum, and at s equals 0, formally that's the sum of the logs of the eigenvalues. And I do it this way so that we have a nice formula for the determinant of a constant times the Laplacian. So if you write this out, log determinant of alpha times the Laplacian, you write the whole thing out, and you will find that the determinant of alpha times this Laplacian is alpha times the dimension of the space it's operating on times the determinant of the Laplacian. That is an extension of what you know in finite dimensions, that the determinant of a constant times a matrix is that constant raised to the dimension times the determinant of the matrix. Whoops. Pardon?
Is there a set of axioms that characterize the regularization?
No, not that I know of. In my first encounter with the way physics does these things, and I didn't understand what they were doing, I adopted this way of regulating, and I found that it always worked.
Well, this is technically called zeta function regularization. We use it all the time.
Yes. All right, now, what I've set up here, coming to the end of this technical stuff in a minute, what we get then is the square root of this operator on lambda 1c perp. That's the stuff perpendicular to the closed forms. Of course, we like Laplacians on the entire space, so we can rewrite it as the Laplacian on the orthogonal complement to harmonic forms on all of them, that is the exact ones except for the harmonic ones, but cancel out the part that's due to the exact one forms, which is the same as functions perpendicular to the constant functions. So I'm really saying, well, let's look at the eigenvalues. So all of these is determined by eigenvalues. Here we have the eigenvalues for the Laplacian on the complement to closed. Throw in the eigenvalues for the exact one forms, and that's the same as the eigenvalues for the functions Laplacian, except for the zero eigenvalue. That is, we wrote this formula down last time. You're just going to take if d starred f equal lambda f, then d starred of df is lambda df. So those two, what I've done is rewrite to cancel this against the part in here that's not already there. I only want to show you where the extra terms, the counter terms, are coming from. But of course, for talking about dimensions, we need more than just the Laplacian. We need to make them have no zero eigenvalues, invertible. Remember, we put in the projection on harmonic forms. If we do that, because we've got the 1 over 2g squared factor in, if we throw that in, then we're going to get these extra terms because of the number of the dimension of h0 and h1. Of course, I could have taken the manifold to be connected, so v0 was 1, but this is what it looks like in general.
Delta would be a product.
Pardon?
You want to project
All I'm doing is making the zero eigenvalues 1. And so that's going to throw in this extra factor b1 times and b0 times in here. So when you're through and remembering the definition of the factorization for a determinant in terms of dimension, we get that this expression is the ratio of these determinants and these raised to the dimensions we want times 1 over 2g squared b1 minus b0 over 2. So what you get here, if you put it all together, is some stuff independent of tau times the imaginary part tau raised to that power. And now you see where that counter terms come from. And then z of tau, I'd put in the counter terms to cancel the imaginary tau to those dimensions. Z of tau then looks like stuff independent of tau times the imaginary tau raised to this power times the theta function we had described before. Now we're finished. Since minus 1 over tau can be written this way, the function tau into the imaginary part of tau to the b0 minus beta 1 over 2, which is occurring there, is modular with this weight. We had the theta function modular with weight beta 2 plus over 2, beta 2 minus over 2. If you put the two together, you get the theorem that I stated. Okay. Now,
This is the whole. What you've done is something was not well defined, and you've chosen a prescription so that you get a certain answer. Modeling terms, and the key point was your definition. You have done a lot of work on that, on lead kernel regularization.
yeah.
But of course, I wonder if this is the right way to do things. But I realize that's more a physics question than a mathematics question. But mathematically, you could also do different things. You want to give meaning to an ill-defined expression. That can be done in more than one way.
I agree. I have chosen a particular regularization, and it's one that I've consistently used over many years. Maybe it's just that I'm comfortable with it.
You get different mathematical answers if you choose a different way of defining things. Are they invariant under your approach?
Since, in order to answer that, as you know, if you had a different one, then you would have to also invent or invoke something like BRST to say that what you're going to get will be independent of the kind of regularization you're talking about.
So it's a somewhat small class, but still the question can be answered.
Yes?
And suppose the answer were different, what would you then say?
I won't answer a conjectural question. Okay.
So there is a question, how does this form out? It depends on the metric structure. Construction of the modular form depending on the metric.
Yeah. The modularity only depended on star. In fact, that's why I did things the way I did. I broke it up into two parts. I used star, and you know, the theta function I talked about and the quadratic form I talked about depended on cup product and star. The rest of it depended on the metric.
All star. Star what star?
In the middle dimension.
But decomposition from all forms.
Yes. The decomposition, the star operator on cohomology, on harmonic forms. What I needed.
Oh, so the option you get just depends on that.
Yes. Well, I broke it up. So the theta function only depended on that. The other part, and in part this will answer your question, the other part which factored out, depended on the metric of the whole manifold. It depended on it in this way. There's a part that doesn't involve tau at all. We don't care about that. That's just a coefficient. The part that depended on tau was this way of defining the dimension, if you wish, of lambda 1 and lambda 0. That's a way of regulating. And that's why it's called a counter term. You just put it in to make things modular. So if there were another way of regulating, you would throw that counter term in order to get something modular. It's what you would do. It's a common thing that occurs, for example, in Chern-Simons. It's not true that the Chern-Simons path integral is independent of the metric. You just check what happens, and there is something that depends on the metric. You put that term in. And then a well-defined term involving torsion and the eta invariant and so on, you put it in. And now, when you put that counter term in, the rest of it will now be independent of the metric.
Yeah, but that doesn't happen. The question is, you have now constructed Riemannian form manifolds as objects. So how does this function of metrics to objects? How does this function depend on the metric?
In a complicated way. I don't know what else to say about it.
For example, if conformally invariant, you multiply the metric by
Yes,
the function, it doesn't change.
Of course.
Well, no, the determinant, no.
No, not so clear.
Not the counter term, it's not clear.
You use star in dimension 1. That's
Oh, the star, only star is what I would say depends on the metric.
Yeah, that's the whole
Just in
metric.
middle dimension.
I only use star in the middle, but the rest of the counter term depended on Laplacian's regularization of dimension for lambda 1 and lambda 0. Well, now I'd like to say a few words. I started about 5 minutes late, so let me talk about what happens for the non-abelian gauge theory. This was really just a warm-up for us because we could talk about something, we can define and prove, but the fact of the matter is that where this comes from is development starting with Montanen and Olive that says there is a duality in quantum field theory between electric charge and magnetic charge. And that duality reflects itself in the quantum field theory for non-abelian gauge theory. So the general statement is like this. You start with a manifold X, and over it you'll have, say, an SU2 bundle. In general, it should be any semi-simple group bundle, P. You're going to assume an action, and here's something which we only began to... Pardon? Thank you. We only touched on this, but we need an action which is called n=4 supersymmetric Yang-Mills. Maybe in my last lecture I'll talk about what supersymmetric Yang-Mills actions look like. n=4 says there's a set of 4 different symmetries for this, and that puts some restrictions on the manifold X, hyperkähler, for example. And then the statement is that the corresponding partition function Z, statement being conjecture, that the corresponding partition function Z depends on the group G, and the partition function is the partition function is the kind that we have talked about, where there'll be the natural supersymmetric Yang-Mills action, complicated, plus a term that corresponds to line bundles, and this will be a decomposition in terms of C2, Pontryagin sectors. And then we will put in constant, so it'll depend on tau, like we did here, the 1 over g squared and the theta. And the state conjecture is that this partition function will be the same as g, z of the dual group, well-defined object for a semi-simple, simply laced group, g dual minus 1 over tau. And then if you double that, it'll say that this particular, meaning if you go back and reciprocate that, it'll say that this particular function under an appropriate lattice of SL2Z is going to be modular of a certain kind. So, for example, if G were SU2, then this should be SO3. Now, the trouble is that the path integrals now are ill-defined. It's a very global statement. You're summing over all different Pontryagin eigensectors. It's just ill-defined. So you don't have a hope of proving such a conjecture.
What kind of dual is that? Between SU2 and SO3?
It's the duality in the sense of Langlands. Langlands dual. For SUN, for example, the dual of SUN is SUN over its center. There's just no machinery to actually check this duality. So what happens is that you look at cases where you can check parts of the duality. So there are cases where this partition function, the semi-classical approximation, is exact, so you can check duality under certain conditions for the moduli space of self-dual. That is, you restrict your attention to a finite dimensional manifold of self-dual and do the path integral on that. When you do that, it turns out that the path integral is supposed to give you, if you were on the kth moduli space, the path integral is supposed to be the Euler characteristic of that moduli space. Again, I say supposed to be because the moduli spaces are not compact. You want to compactify them, and then you want to get the Euler characteristic of the moduli space. Now, having gone that far, then what this partition function is, as a function of tau, is the Euler characteristic of the kth moduli space, e to the 2 pi I tau, k tau. This is sort of what Z is supposed to be like in the semi-classical approximation, and there is good reason that the semi-classical approximation should be
What is that sum over?
this is sum over K, the Pontryagin sectors. K is C2 for the line bundle. So that's what it's supposed to be like, and therefore you're led to the conjecture that this should be modular. Okay. Now the point I'm trying to make is by sequence of educated guesses, you're led to a mathematical conjecture that this should be a modular function. Lo and behold, for Calabi-Yau's, this has been proved. I didn't bring the references with me. They're upstairs. It's been proved for Calabi-Yau's, for CP2, for ALE manifolds, all very special manifolds which some cases have a lot of symmetry going for you. This conjecture has been shown. And so the flavor of much of duality from the mathematical point of view is that you don't know what the field theory looks like. You can get pieces of the field theory like there, and then they become conjectures, and you now turn them over to experts and see what experts by these conjectures, and lots of evidence for the duality, that for S-duality in Yang-Mills.
This all arises from the duality between electricity and magnetism.
Yes, and now, so I'll make two comments about that. If you look at the action I wrote down, you'll see it's invariant under star. And if you look at the equations of motion, the equations of motion is d star f is 0, and at the quantum level, you want that to happen as well as df. So f and star f play the same role. In fact, if the audience felt comfortable with the curvature. So this stuff, what I've talked about, is invariant under star. And that's the reflection of electricity versus magnetism. And in fact, if we were comfortable with the formal manipulations of path integral, I could have given a sort of a 3-page proof of duality without the computation, rather than give a mathematical proof. So what I wrote down is invariant under star. If your 4-manifold is a 3-manifold cross time, then star reverses, interchanges electricity and magnetism. And now that allows me to end with an advertisement for my next lecture. I want to go back next time and talk about the basic observation that led to S-duality of Montan and Olive, showing you a simple quantum field theory and how they conjectured that electric charge and magnetic charge should be reversed. I remember listening to Olive when I first heard him in England many years ago, and I was absolutely flabbergasted at the idea that electric charge, which was representation theory, representation for the circle in this case, that discreteness of the integers, was going to be reversed dual to magnetic charge, which was topology, a winding number at infinity of a two-sphere. That those two played dual roles was, I thought, a very striking conjecture on flimsy evidence. And that's what people thought at the time, but over a period of time it now has been formalized into this well-defined conjecture of S-duality. But I'll go back to that simple example on Tuesday. Thank you. Questions?
Are you saying that somehow the local form of S-duality is just invariant to the star operator? Somehow all of this local phenomena can be understood as...
I don't know what local form means.
Well, I mean, that's local geometry. Star operator is a local operator, right?
Yes?
Somehow. Is that really the... Underlying all of this is this ability to replace F by F star in what you're looking at? This is a very vague question.
Bring it up again next time, because you see, it's... Peter, I'm not a physicist, so I'll make a statement, and we got a couple physicists perhaps can say more. Really, to me, what's happening is on a quantum level. You know, on a classical level, there is a difference between F and star F, because d star of F is not 0. It's going to give you the current, and in the world we see, they're really different. It's at the quantum level, as you'll see next time, that you can begin to hope, or you begin to see, a duality between electric charge and magnetic charge. That's the way I see it. I don't... You could if you're willing to put in sprinkling magnetic monopoles, then you could put F and star F on the same level. You could actually do that, but I feel uncomfortable with doing that classically.
Suppose I'm starting here with a certain amount. Like, how can you predict that the quantum field theory will satisfy S2I? I'm just looking at an atom. What are the good? What is special about the quantum interactions that makes you think that the theory will be?
Well, it's just, for example, originally they didn't have any supersymmetry. And then you might think it was n equal 2 supersymmetry. But no, you need n equal 4 supersymmetry. And you can look at, where's the best discussion of why you need n equal 4 supersymmetry? It's probably in Vafa-Witten. It might even be back in a very important paper of Olive and Witten, where they take the supersymmetry Poincaré, the supersymmetry algebra, and have to take central extensions of it in order to make this idea work. So I think n equal 4 supersymmetry is what you need.
Do you have transparency? Could you put it back up?
Which one?
The very last one. It had that fascinating series of coefficients of Euler characteristics on the space.
Yeah.
What was the group that was always SU2?
Yeah.
So these are for
These were verified only for SU2. Now, yeah, what I haven't kept up with this development. There's so many other developments. I haven't kept up with this one over the last year. So the issue is what's happening with other groups. People were working on it very hard when the Vafa-Witten paper first came out, which made the conjectures and explained what verifications they were. They really, actually, what they did was take the quantum field theory, twist it, what's called twisted it to get a topological field theory. Then you're in a realm that's mathematical. And then these partition functions are the Euler characteristics. And it's on the basis that they made the conjecture and told what the verifications are. I can give you a reference for that paper.
These Euler characteristics are of some compactification or not at this space?
Well, they don't say, but that's what they're supposed to be.
Characteristic of some specific compactification, or is it just the space itself?
No, I believe it's of some compactification. For physicists, it's a formal integral restriction of the path integral on this space.
To make topological sense of it.
And it should be the Euler class. And again, for good reason. If you know the Mattei-Quillen formalism for equivariant cohomology for the Thom class and Euler class, then what you finally end up with after the twist is exactly that formalism in infinite dimensions. You expect the restriction to be the same. But, I mean, that's a big machine in itself.
The funny thing is that mathematicians use different applications of these moduli spaces, and they typically have different Euler characteristics, right? I mean, and it can blow up at infinity. And
well, I don't know which one is meant. I don't think they're finite. I think you really have to compactify. One would have to look at the reference to see what they actually do.